So when methyl bromide reacts with hydroxide, methanol forms, and the rate law, that is the kinetics, really tell us that this is a second order process overall. Whoa, there's a lot to unpackage in this problem. Let's dissect this thing a little bit and just kind of see what's happening here. So first and foremost, we'll identify a couple of these characters here. We've got methyl bromide, and so methyl bromide it's this guy that's right here. And we've added a few stereochemical elements here. Stereochemistry will be slightly important in this unit, so it's important for us to know that. And then we have hydroxide. We might as well highlight that as well too. That's going to be your OH right there. And what do we make in the process? We make methanol. This is a chemical fact. This is what's going to happen. If you take methyl bromide and you react it with hydroxide, you're going to make methyl alcohol. That's your methanol. That's right there. So let's kind of see what's happening here in this particular chemical reaction. So what bonds are being broken and formed, right? Let's do a little bond accounting here. So the first thing you might notice is that we break this carbon-bromine bond. So when we're talking about this, we are breaking a carbon. This is an sp3 hybridized carbon, Br sp3 hybridized sigma bond. The fact that it's a sigma bond is vitally important here because that is kind of a characteristic of these types of chemical reactions. Okay, well, what are we forming? Well, in this chemical reaction, we're forming a new oxygen-carbon bond. Both of these atoms are going to be sp3 hybridized in this particular example, and importantly, it is a sigma bond. So what's the important detail you should recognize? Whenever we have a chemical reaction where we are breaking a sigma bond and then forming a new sigma bond, this is, by definition, what we call a substitution reaction. So we'll abbreviate reaction RXN here. So what are we substituting? Well, real plainly, what's happening is that we're substituting that bromine atom for an OH functional group, an alcohol functional group that's in here. That's what we're substituting in this case. Again, break one sigma bond, form a brand new sigma bond in this case. So let's look at some kinetic data and see if we can kind of understand what's going on here. So if I were to run this experiment, just go into the lab, create a 1 molar solution of hydroxide and a 1 molar solution of, what do we have here? Methyl bromide. What is the relative rate? Now, the relative rate doesn't have a unit on it. It's just giving you just kind of a for instance here. We could assign it a value of 1, but that's our baseline measurement. That's our reference point we're going to take a look at right here. What happens to the chemical reaction, though, if I were to increase the concentration of hydroxide from 1 molar to 2 molar? So we're looking specifically at this instance right here. Well, what's happened to the chemical reaction? When we increase the concentration of hydroxide from 1 molar to 2 molar, the rate increased. So when we doubled the concentration in sodium hydroxide, or hydroxide for that matter, we also doubled the reaction rate. And similarly, if we do this for tripling the concentration relative to the reference value, the rate triples. Look at that. Kind of cool, right? So what is this telling us right here? Well, it's telling us a couple different things. Kinetically, we know that the concentration of HO minus is proportional to the rate. What does that mean? As I increase in the concentration of HO minus, I necessarily increase in the rate. So that's HO minus right there. What's going on with the methyl bromide? So let's take a look at that example here. So this will be, I guess, our fourth row down here, about there. So in this experiment, what do? We hold sodium hydroxide, or we hold hydroxide constant, 1 molar, and then we increase the concentration of methyl bromide. What happens to the rate? It doubles, right? So as we double the concentration of methyl bromide, we see a doubling in the reaction rate. Okay, so this is telling us an important clue, and you can probably make a prediction, right? So if we triple the concentration of methyl bromide, we triple the reaction rate. You can see that right here. We triple relative to the reference reaction. So what is this telling us? Well, this is telling us yet another relationship. That is, that we'll abbreviate methyl bromide, MEBR. MEBR is proportional to the reaction rate. In other words, as we increase in the concentration of MEBR, we are increasing in the rate. So the two of these are related. So now the question really starts to become, what happens if I increase the concentration of both of them? So if I look at the reference point and I look at this last reaction right here, and I double the concentration of hydroxide and I double the concentration of methyl bromide, what happens? We have quadrupled the reaction rate. So what is this saying? This reaction is very, very sensitive to both the hydroxide and the methyl bromide in this case. Now, in these instances where this starts to happen, this is, by the way, this is an exponential relationship, but where this starts to happen is that we can see that the rate of this particular reaction is proportional to hydroxide and methyl bromide. And you may recognize an expression that looks kind of something like this. We're not going to really harp on the math too much in this instance, but you may remember this from Chem 2 when we look at kinetics. And you know that this looks kind of like a rate law, and a rate law is a mathematical expression that relates the reaction concentrations, the reactant concentrations, to the reaction rates. You remember that there's always some sort of an exponential descriptor for this, right? This is what we call the order. And so in this instance, the order is 1. So you have the initial concentration of hydroxide is raised to the first power. Methyl bromide is also raised to the first power. So the overall order for this process is 2. And so what does that practically mean here? Well, it's telling you that this is a second order process overall. Practically what that means is that for this chemical reaction to proceed, hydroxide has to bump into methyl bromide. Now, this isn't the complete rate law. The actual complete rate law is going to include a constant. So we'll put the actual final rate law for this chemical reaction. And this is what is going to describe this particular chemical reaction right here. This is the rate law. So we can more or less boil away everything else in this chemical reaction except for the reactant concentrations. Those are the two most important things. And they tell us that as we start to increase them, they have a direct relationship, individually have a direct relationship on the reaction rate, but together they have an exponential rate on the chemical reaction rate.